What is up, YouTube? Welcome back to another video. It's your boy Zephyr Smith back with another physics lab. Today we're doing magnets. So this lab was designed to help model the magnetic field that comes from a bar magnet with using Coding Bat online coding software, which approximately models a dipole charge. All right, so we use the distance dependence formula and the magnetic field of a bar magnet. We use both those equations in order to determine this. My conclusions were that the magnetic moment of a bar magnet was 3.33 amperes times meters squared, and that N was negative 2.74. Okay, so as I said, the model we're using, it's approximately the same as a dipole. Yeah, and so the initial conditions, we got the bar magnet, which is next to a meter stick, and we've got the magnetometer on my phone. And so the system, I chose to be the magnet and the magnetometer, and the surroundings were everything else, including the Earth. So I slid my phone in the y-axis in order to find where the X charge was the greatest, and that marked where the magnetometer was the closest. And I did the same thing sliding it in the X direction, and I used that to pinpoint the magnetometer on my phone. I then found the distance at different charge values and I plotted those on a graph. You can see I did 20 microteslas, 70 microteslas, 120 microteslas, 170, and 220 microteslas. And I graphed those, took the natural log of both sides, and that gave me a linearized version of my graph, which I can use in the distance formula. I then measured the horizontal distance that made the electric field 100 microteslas, and then I moved the phone up vertically that same amount, and I took those measurements and I used that to calculate the net magnetic field off axis at a 45-degree angle. And I also had to take into account the Earth's charge since we are now off axis. And so my calculations, I used the distance dependence equation, and the equation I got from my graph, y equals negative 2.7364x minus 14.222, where negative 2.7364 equals n, and negative 14.222 equals the natural log of k, where k is now 6.66 times 10 to the negative 7. And I set our equation right there equal to the distance dependence formula, and I solved for mu, where I determined that it was 3.33 amperes times meter squared. And this is my glow script. It's really nothing crazy. We just got a function that gives us the charge at some vector from a dipole. We we make observation locations and then we make arrows and calculate the charges at each of those locations. Pretty simple. And so you can see in my model, I've got all those locations and I've got it marked by B axis 1, 2, and B per 1, 2, 3, 4. We've also got the distance to the off axis location, and we can see the magnetic field at the off axis location, even though an arrow did not show up. I don't know why the arrow isn't there, but you can see I got the vector, should be there. That's beyond me. So the theoretical off-axis field, I got 1.19 times 10 to the negative fifth, which is only about 20% of my recorded value, which was 6.31 times 10 to the negative fifth, but it's in the same, order of magnitude, so I'll take it. So what are the sources of error? My magnetometer could have given me a reading that's not completely accurate. It is a cell phone after all. The location of the magnetometer could have been slightly off, just due to my measurements, so that would lead to the rest of the measurements being slightly off as well. Or the magnetic field from the Earth could have also been measured slightly off, which would also lead to the rest of the measurements being slightly off. And so, what I know what you're thinking. What if I hadn't oriented my experiment to compensate for magnetic north? And I would say that's a great question. At that point, we would have some magnetic field from Earth at some angle, and then we would have to account with that, and it would take more equations and it would take more effort. And I'm glad I didn't have to do that. And so, what if I was to stick two identical magnets together end to end and run the experiment again? And again, I say that is a great question. How would that affect my measurements? I think that would just about double my measurements, really, because they're not exactly in the same spot, but due to superposition, I think the measurements will be approximately double. Anyways, that is all for today. If you like what you see today, make sure to subscribe. Make sure to hit that bell icon so you can be first on my next physics labs. All right, take it easy, y'all.